Sí.
Yeah.
Yeah.
Okay, I will talk about a zero order scheme. The new scheme is called a zero order and conditional positive and conservative modified Patanka-Runge-Kutta scheme based on Oliver approach. Tells the cons. I will talk about three topics. First topic, zero order Runge-Kutta Oliver scheme. Next, the new third order modified Patanka-Runge-Kutta Oliver scheme. Finally, numerical results. Runge-Kutta Oliver scheme is zero order if A equations are satisfied. These equations are from Pythagoras. If C1 is 0, equation 7 and equation 8 reduce to equation RK2 on the right. And equation 7 and 8 are the same if only if C2 is A to 1. If C3 is equal A31 plus A32, this equation green reduced to equation RK4 on the right. Similar, read equation reduced to equation RK5, and this equation 1 is the same equation RK6. This equation will the modified Patanka-Runge-Kutta scheme. If C1 is not 0, green equation reduce to O4 equation on the right. Green equations are the same if only if B1 is 0, C2 is A to 1, and A31 plus A32 is equal C3.
Is this a requirement, or is it that B1 should be 0? Is this a requirement?
Requirement.
Okay.
The equation reduced to O5. And A equation is the same O6 equation. And equation 7 reduce O7 equation because using A equation into equation 7, this part is 1/6. Therefore, equation 7 reduced to O7 equation. This equation on the right are condition order for new scheme. nonlinear system solution. In the plane, C2, C3. The system line and ellipse has two solutions, C2 and C3. We consider three possible cases. Case 1, 0 less than B2 less than B3 less than 1. Case 2, 0 less than B2 equal B3 less than 1, and 0 less than B3 less than B2 less than 1. The picture shows the case. Case 1 is in green, case 2 is in red, and case 3 is in blue. From two solutions for each case, only one satisfies equation 02, 06, and 07. In the case 0 less than B3 less than B2 less than 1, the solution is C2 equal 1/3, C3 equal 1, A31 equal -1, A32 equal 2, and B2 equal 3/4, and B3 equal 1/4. Except from C1 equal beta, single parameter in the Butcher table, we have a unique solution for the remaining value of the Butcher table. The new scheme, modified Patakar-Runge-Kutta-Oliver scheme, is the following.
Okay. Could you please go back one slide and show this Butcher tableau once again? So this is the Butcher tableau you want to build your schemes on, right?
Yes.
Yeah. So there's a negative parameter -1.
Yes.
So how do you deal with that? Usually we have positive parameters.
Okay. The question to A, to B, to C, to D is similar modified Patakar-Runge-Kutta. The main difference is the new beta in the first and second stage.
Mm-hmm.
Another difference is negative coefficient. By Taylor expansion, this term is minus PIGN más other terms. This production, 2 PIGN más other terms, is the sum, the production terms is PIGN, if this term is positive. Similar deduction by Taylor expansion.
But this is only positive if delta t is small enough. Because otherwise this dot
Could be
area.
Yeah, we agree.
Because you have PIJN plus something which is capital O of delta t. So if delta t is really large, this capital O of delta t could be large as well.
Yes.
And it could be large and negative in the sense of the absolute value is large, not the value by itself. And at the end, PIJN plus this value within capital O of delta t could be negative. And we are focused on schemes where you can use delta t as large as you like. But we know exactly that at the end of the game, we have to choose delta t in a manner that the resolution of the physical quantities or whatever you are searching for is good enough.
Okay.
Okay, so let's continue and then we will see some idea. Okay. But we agree with you. I mean, it's not a problem. It's just the Taylor expansion, so we have to be careful.
The compute the weights is similar al modified Patancar-Ronji-Kuta scheme. PA, rho A, mu A is similar. To compute the weights sigma I, we use a second order Ronji-Kuta-Oliver scheme. Similar modified Patancar-Ronji-Kuta. In this part, beta on the right, alpha 1/3 in the on the right. For C2, use alpha minus 2 alpha beta plus beta. Then C2 is beta plus 1/3. And beta 2 is equal 3/2.
D2.
Beta 1 is beta 1 is minus 1/2.
Yeah, and just a question, Javier. Now the third order MPRKO scheme is different to the one you have shown us before. Different in the sense that the B values are different.
They are not the same.
Yeah, because here, if you go back, once, okay, here you have B2 is 3/4 and B3 is 1/4.
Yes,
and in the table you have shown us -1/2 or so. Here, it is -1/2.
Left, yes.
Okay. It's error.
It's an error. Okay.
See.
Okay. That's
okay.
Okay.
Similar by Taylor expansion for delta t is more. This term is PIGN plus 3/2 PIGN. The sum is PIGN positive. T's turn. I think in this way, the matrix in each stage will be M matrix.
Do you think or do you prove?
So the proof.
Tabro.
Mhm.
Okay.
And finally, result, numerical result. First model is simple linear test tank. The table shows the first scheme is the best.
Mhm.
And the compute show the new scheme is third order. Second model is third model. The tariff shows the first scheme is better when delta T is less than say 0.117. Also, the compute shows new scheme is third order. The next case, Brusselator test. Again, new scheme is the best. Also, reach third order.
So the Brusselator test case does not depend on time. It's autonomous, right?
Yes, the Brusselator.
So you can find some MPRK without the O, the original scheme, which produces the same result as your MPRKO scheme, I guess. So if it's not dependent on time, so the Oliver trick
Will not fit.
doesn't do anything. So they should be
The same.
equivalent of our old schemes. Yeah, just as a comment.
Yeah, sure.
Yeah.
I don't know why the error is different, but anyway.
Yeah, the errors are different because the A parameters are different.
Okay.
Yeah, and even also the
Oh,
B
it's-
parameter. So
Yeah, sure.
it is not the MPAK, the Oliver approach does not converge to the general Runge-Kutta approach in the case that it is an autonomous differential equation. Because the A and the B parameter are different. So one can use the Runge-Kutta method with other C parameters,
Mhm.
and then one should get the same results, but he's not doing that.
Okay.
So it's quite clear that he has to have different values.
Okay. Nonlinear model test. Again, the first scheme is the best. However, in linear jack stack,
Mhm.
the first scheme does not reach third order, but second scheme is third order. Finally, Robertson test, good solution for new scheme. Thanks.
Okay.
Okay, thank you very much, Galo. Questions, comments?
Yeah, I have a question concerning this one and only butcher tableau for third order Runge-Kutta-Oliver schemes.
The one with the number, that one or
No, the first one.
that one? That one.
Yeah, that thing. So if you don't think about Oliver, if you talk about real Runge-Kutta third order schemes, then there are 3 different types of families. One is or 2 of these are 1 parameter families, and there's 1 2 parameter family. So there are infinitely many third order Runge-Kutta schemes. And now here we see that if we apply Oliver's trick or whatever we call it, then there's only 1 third order Runge-Kutta-Oliver scheme. So this is, yeah, I didn't expect this. Yeah.
We too. We too.
So,
Expected to have only one scheme.
Is that known from the literature?
No,
No.
no. So yeah, that's surprising that you get more and more restriction instead of having more and more parameters. You relax something and you get less schemes.
Okay.
Yeah. So we agree with you, Stefan. Really, we expected more to extend.
So, yeah. Okay. And then the next comment is if we could go to this the scheme, the new third order scheme, to ensure unconditional positivity is now in this equation 2c, where you have the minus in front of the Pij. Yeah, so if you have a negative Runge-Kutta parameter, then your production term becomes a destruction term. Now it's negative, and vice versa. Your destruction term becomes a production term because now its sign is positive. Yeah, and then I'd suggest you should multiply this minus Pij term with the Partanka weight with an I, yi3 over rho I. Yeah, so usually you multiply destruction terms with these Partanka weights with index I and the production terms with index J. And now because of the negative Runge-Kutta parameter, production and destruction change, and then you have to multiply your P term with the Partanka weight with index I and vice versa for the destruction term.
Negative with I, negative with I, positive with J.
Yeah, right. So if there's a negative parameter in front of a production term, now this becomes a destruction term. Yeah, and this will give you an M matrix, and then you will have unconditional positivity.
Yeah, and independent on delta T.
Right. So that's the trick.
Yeah.
Okay. Okay.
Yeah. So I believe that if the delta T is not that large, and the production as well as the destruction terms are not that small at the time level Tn, then even also in your case, Javi, you will have an M matrix. But from my point of view, I expect that you could not ensure that for arbitrary delta T. But if you change, as Stefan mentioned, then everything is clear. And for each delta t, you will have an M matrix and everything will work fine.
Even for small delta t's, this can be negative.
Yeah, for sure.
Yeah.
It could.
Yeah.
The Taylor expansion and
And
everything.
y1 and y2. So
In most cases, there will be an M matrix.
Yeah, but this is math.
But
This is
you're
not physics.
You're not sure every time.
Yeah.
Huh? Okay.
We need to be sure. Okay.
Okay.
So,
Mhm.
And that what Stefan mentioned is also always the idea. If you could not know in advance the behavior of the right-hand side of your differential equation, so there are some terms who could change their sign in time, then you always have to decide, is it a production or a destruction term from time step to time step? And depending on the sign, you will say, okay, I will weight them with the PVD with I or with J. So then it will appear on the diagonal or diagonal in the M matrix.
cuando cambian de signo. Acuérdate que
Mhm.